Welcome to the last lecture in the deep learning course. The topic of the last lecture is reinforcement learning. So the objectives of today is to first, as usual, understand what we are talking about. So we will understand reinforcement learning, what it is and what it can be used for. And then I will take a case story to illustrate what a practical application of reinforcement learning for the game Go, and taking a walk through DeepMind's AlphaGo system. Then we'll get a little bit formal and talk about policy gradient methods, which is arguably the simplest way to understand reinforcement learning. And then I will finish up with some final words about deep learning and other things. Reinforcement learning. So reinforcement learning is about the situation where we have an agent that can take actions in an environment, and these actions will affect our future rewards, our future outcomes. So good examples of this is of course in games where we play chess, for example, and we have a system, we have a computer system to play chess, or we play chess and we make a move now that can be fatal for our chances of winning the game, many steps ahead. And we can also think about traffic. We take actions in traffic and that will affect whether we will make a collision some seconds from now. Yes, so let's learn the words to formalize reinforcement learning. The first concept is the state. So that is the state of the environment. So you can think about a game like chess or Go, then it's the board position that defines the state. In this state space we can take actions, we call those A, and there can be an infinite number of actions possible or finite number of actions. We usually discretize the space of actions, so you can think about A as all the possible moves we can take at a given time. Then we have a dynamical environment that takes the current state, our action at time t, and then it updates the state. So we think here about a discrete time system. We also have an instantaneous reward at time t plus 1 that can be a function of both the state and the action at the previous time step and the state at this time step. And then we have some observations. Usually we'll have a fully observed system, so we observe both the state and the reward at that time step. But we can also imagine that we don't observe the full state of the system. Then we have a policy. This is where which we use to make decisions about what actions we'll take. So you can think about it as stochastic. So we are given a state and then we have a probability distribution given this state of taking one of the actions. So we call this policy pi. And then we have a reward, so that is how much we at the time t, and in the future we will accumulate a reward, and we usually also work with a discounted reward. So we have this gamma factor, and gamma is usually less than 1. So that means that rewards we get closer to the present and not so far in the future will count more for our cumulative reward, which is sum of all the instantaneous rewards over time. And then we have in the end we have an expected cumulative reward. So we take the expectation of this capital R over our realizations of the dynamical system that we have here. Yes. So, okay, so just go back here. So this formalizes the kind of system we have, and what we can change here is we can change the policy that we use to make these decisions of what actions to take.